Our project is the anatomical characterization, simulation, design, and test development for an implantable pulse generator and lead. We are from the Biomedical Engineering Department, and we are sponsored by Biologics. In the United States, 70% of adults over 65 have high blood pressure, and many of those do not have it under control, putting them at risk for other cardiac events. The sponsor's goal with the device is to create a closed-loop baroreflex system to treat uncontrolled high blood pressure by connecting an electrode to the carotid sinus nerve and supplying electricity to restore native function. Our task as a team is centered around the lead and the path it takes. As a team, we were tasked with first characterizing the length and force changes of key muscles in the neck, then determining the relative motion of the lead during neck movement, and then lastly, providing any necessary lead path recommendations to aid in the sponsor's development and understanding of the desired lead path for their device.
For this project, we took two approaches, a physical model and a computer simulation. Our physical model had multiple generations, increasing in accuracy with our final generation using Syndaver synthetic muscle tissue sheets, allowing us to physically measure the changes in distance between the SCM and the carotid sinus, compare data sets within the different generations and movements, and provided us a tactile way to test and determine lead path placement and pathing. The computer simulation utilized a pre-created OpenSim model that had rod-like muscles and generated plots, allowed us to add reference points at the carotid sinus, and gave us more data to compare to the physical model.
For this project, we made 3 models. Generation 1 was made of 2-way stretch fabric and demonstrated how 11 different muscles related to one another in 6 different mechanical movements. The second generation used exercise bands as muscle representations. Our scope narrowed to just the SCM and the anterior, medial, and posterior scalings for testing purposes. Generation 3 was made by using Syndaver muscle sheets. For this model, the team only created the SCM and the carotid bifurcation for testing, then later created the scaling muscles for lead pathing.
OpenSim is an open source software used to test kinematic and dynamic motions of the human body. For this project, we used OpenSim to identify the lengths and tensions of each region of the neck in an effort to identify potential muscles for suturing and pathing of the lead. After the muscles of interest were identified, OpenSim was used to help provide data for distancing between the carotid artery bifurcation and the muscle itself. Then this data was compared with the data from the physical model to test for accuracy and provide supplemental information that was consistent. Data comparison between the physical model and the OpenSim model showed that the trends for each movement were similar. The left cervical rotation, the trend showed that an increase in distance between the baseline position looking straight forward to the 60-degree head turn. The percentage of increase in this movement was 10 to 13% from baseline between the 2 models. For cervical flexion or looking downward, we saw a decrease in distance between the 2 models used during, specifically a 14 to 16% decrease from baseline values.
Looking towards the future, the team would like to improve the physical model attachment points, potentially purchase a custom muscle model, and increase the amount of head movements tested. In terms of the computer simulation, the team would like to fabricate our own computer model with customizable demographics and more controlled variables. Lastly, the team suggests collection of durability and cyclic testing to determine lead strain over an extended period of time. The team would like to give acknowledgements and thanks to faculty advisors Dr. Jiang and Dr. Yu, Biologics sponsor Mike Griswin, financial support to Michigan Technological University and Biologics, and purchasing support to Devin Sapla and Alexandria Holstrom.